Thanks a lot, and thanks for the organizer for inviting me. So I plan to talk about branching random walk in high dimensions. So I know I have to stick to high dimensions. I'm going to speak still about simple random walk, which I like most. So a simple story about excess folding. So that's the main theme. And I added that I will also talk about more things like percolation clusters. And there is some unifying objects. So what's the motivation? I want to estimate the probability that two transient processes meet a lot. So you have the first one, and it's transient, and you take another one, independent, starting from the same place, so that typically they would not meet often, but you want the tail of so you look at the points which are both red and white, you compute their volume, and you want this to be large. So you want the tail of the number of intersection of the trace of two independent transients. So I want two independent transient trajectory. And typically, that's the problem I'm interested in. Yes.
Are you doing synchronous meeting or asynchronous?
No. So let me say that I'm looking at the set of sites which have both colors.
Uh-huh.
So that's.
Because then the transience is not the relevant notion, is it?
Why not?
Because if you take two three-dimensional random walks, they're transient and they'll meet infinitely often.
Yeah, but I want them to be very transient. So you're right. It's not enough that they are transient. I want that the expected number of intersection be finite. So I'm going to take them in higher dimension, 5 and more for the simple random walk, and for branching 8 and more, strictly larger than 8. So you're right. So let me say that. Well, let me write it for 3 models. Same question, but it's going to help me to set the notations. So the first model is simple random walk. And ZD. Okay, and so what's a simple random walk? We saw just a talk just before of Sarai where she defined simple random walk. Let me write it this way so that it's going to be a little bit strange, but I have time, so it's a process indexed by time. On the edge, I put some increments, so I have all my stacks of independent increments who lives on ZD, and I send it to ZD. So time 0 is sent to a site here, X. My process is, I'm going to write it this way. S at 0 is X, and S at n plus 1 is Sn plus the n plus 1 increments. So that's my random walk. So what you have to know about random walks is that it takes about r square step to go out of a ball of radius r. So let me give you let me justify heuristically why Marek is correct that you have to go to dimension 5 and more. So each walk is going to spend the time r squared to go out of that. So the density that it leaves is about, so the one makes a density r squared over rd if I am in a ball of radius r. And then you send the other one. And you might say that the intersection of the range, their intersection, is going to be about how many times the red one spent there. I wanted to write it in red, but okay, let me write the r squared in red. That's the amount of sites visited times the density if they were uniformly distributed, I would get. Okay, so I want this to be small, to be a small number, so I need dimension to be larger than 4. Okay, so let me use more notation. R is my range, set of, and what I really want is the intersection of the two ranges in dimension 4, 5 and more. Okay, so this is linked with, if this is, I'm not sure if finite, if the square of the green function is finite, and what is the green function? Is the expected number of visits to site X. Okay, so it's the expectation of the local time. So I would need this notation, so let me introduce them. So it's the expectation of my local time S starting, let's say, at 0 of X. So the names are local time, and this is Green's function. Okay, and the question is this one. In infinite time, what's the chance that they meet often, and where are they going to meet? Can you describe the scenario there? Okay, that's the simplest model. Let me go to something more exciting. Branching random walk. So branching random walk.
Are you going to tell us the answer?
Yes. I will write the answer for all the models. And you'll see that they all look the same. Yeah, all the answer looks the same. So that's the nice thing about it. Branching random walk. So instead of my time being a line, I take a Galton-Watson tree. But the tree is critical. That is, on the average, each one has one kid. Okay, so that's my genealogy. And here again, you will associate to each edge an independent increment. So that's your stack of independent moves. So what you do is you embed this on ZD again. You send the ancestor somewhere, X. And whenever you take an individual here, you follow its ancestors to find the position where it should go. So my notation is that T starting at X, C for critical tree, and that's the position, let's say, of individual U. Not sure it's going to be the X position plus the sum over all the edges between the root, let's say, and U of the increments. Okay, so it makes, you have a cloud of points, of random cloud here. And you see what, if you, okay, so I can define the same type of object. L tau x critical at a given site Z is the number of visits. So I have to say that critical means that each one has, on the average, one kid. So you know that this tree is almost surely finite. So this is, and that's well defined. It's the number of visits of Z. And the expectation of this number, can write it this way. So you count on the generation. For each generation, you count how many given generation is going to give. So let me call Zn the population at generation n, to stick with undergraduate like courses on branching. You belong to Zn. And I'm counting if my tree at U equal Z, And when you take the expectation of that, there is, on the average, one person, one individual at each generation. So the green function you find is the same as the green function for the random walk. Same as random walk. So, but the question I'm asking is about long time behavior. So this tree is not that relevant. I mean, what I need to think of is the tree condition to survive a long time. So rather than looking at TC, what's important is to look at the tree knowing it has survived a long time. Okay, and there is a way to take this. This is well known. When you take the limit of this tree, you can find the Kesten tree. But I'm looking at another infinite tree, which is going to be invariant under rerouting. It's like a tree seen from a uniform vertex. So you go to some infinite tree, and don't want to which is going to be. Let me just make a drawing of this tree. This is a one-handed tree with a spine. So there is an infinite spine on ZD. Looks like a random walk. And there are critical trees spanning from its vertices. I should draw them with different colors. If I want to label my tree. So that's the direction of time. This is the future trees. And on the other side of the spine, that's my 0. And on this side, there is the past of the tree. So you end up with a structure of an infinite invariant tree and a rerouting of the root. And this tree is going to be important for us. OK, so now, what do I want to say is that intuitively, if you condition your tree to reach, even your critical tree condition to reach the boundary, then you know that it will, I mean, when you think of one trajectory which touch the boundary, it needs a time r square. So typically, when this happens, it means that generation n square is positive. And under this condition, you know that there are about n square individuals arriving on the tree. So most of the time, it's not going to reach that. But what I have to tell you, the probability that Zn square is positive is about 1 over n square. And so knowing that the expectation of Zn is 1, you know that knowing that you survived, Zn square is of order n square. And so knowing that you have survived, you have about n squared times n squared sites which are occupied. So the tree inside is going to be or maybe I put here whatever, the infinite one or the TC condition on living. So TC condition on touching the boundary. Touching the boundary is of order r squared. So r to the 4. Because I have n individuals, which each one, you can think of them, they are not independent, of course, but think of them as each one being a simple random walk. So each one is going to cover a region n square of space. But if you don't like that, I can give you maybe, I try to be, just to give some intuition about this process, but we can compute the green function of this. If you accept this computation, or what's the green function of the infinite, of my infinite tree? See, so you have, I'm doing something very rough just to get the correct powers of R. So that's a simple random walk on which you have critical trees. So if you want the expected number of visits of sites Z, you sum over the sides of the spine. You sum over the position of your spine, and then you compute how many visits, the number of visits of my tree. So I write it this way: of my critical tree starting at Y, Z. We saw that this was just green function, and this is again green function of Y. So you have the convolution of J star J, which is of order at a given site Z is of order Z to the D minus 4. So you have a green function decaying like D minus 4, and so the average time spent is R to the 4. Okay, second model. Let me go fast about the third model. Independent bond percolation on ZD, D very large. And I look at the critical percolation. I look at PC. We know that the cluster at 0, so that all the site X for which there is an open path, I'm linking X to 0. We know that this is almost surely at PC finite. Okay. And we know that the two-point function is like green function. So the probability that you link is of order 1 over x to the d minus 2. This reminds very much of the critical tree, this thing, same green function. And I can take the limit of this object when I condition on hitting some boundary. So imagine that's not maybe the way it was done by van der Hofstadt and Yarai, but it's believed to be true that when you condition the cluster to reach the boundary of this ball, so let me give the following statement. At PC, imagine you take a site, it's not exactly that, but a site far away, and you want it to connect with 0, and you want the cluster at 0 to contain also site X. You divide by the probability that Z is connected to 0, and this has a limit. And this defines the infinite incipient cluster. So there is something which looks very much like what I was taking the infinite limit of my tree, which is what I will call the infinite incipient cluster at 0. So that's a probability that it contains site X. Okay, so 3 models which look different. Let me say that for the infinite incipient cluster, the green function is the same. The probability that it contains site X decays like 1 over x to the d minus 4. So this was van der Hofstadt and Yarai. So this looks very much like branching random walk. So now the results. What are the results? Let me try to not results. So I mean I'm greedy with the references. I'm not giving names, but all these results have a long stories. So I'm trying to give you some of the key papers, maybe. The first thing for simple random walk. So all my objectives are going to be that. For simple random walk, that's where we have the most complete results. That's a certain density, which I will call BBH, time, I write it this way on purpose, a new object, the capacity of a ball of volume T. And written like that, it might not mean anything. I have to define this capacity. And this means that you have a correct constant upper, and it's a large deviation principle. As t goes to infinity, and this result, I have to first say that it was Hanin, Mazel, Schlossman, and Sinai. 93 got correct factor here, but not the constant. Then Vandenberg, Bolthausen, and then Hollander in 01 looked at a finite time. They could not do the infinite volume, the infinite time horizon. So it's as if you were confined in some compact space. And finally, with Bruno Shapira, three years ago, we obtained the infinite volume limit. So, and we know much more. We know the scenario, but let me go slowly. And then that's for simple random walk, in which in dimension larger than 4. For branching random walk, same thing. Start at 0, take the critical or the infinite one, it doesn't matter. So I'm not going to rewrite this all the time, but and here we don't have, so I should say something like that. We don't have the same constant. We don't know what's the correct constant, but we have the rate at which, and this is not the capacity, but the branching capacity of the same ball. And for the intersection of two infinite incipient clusters, which are independent, we only have the upper bound. So yes, we only have the upper bound. Exponential minus, and the constant, let me write it this way. And it's something which scales like the branching capacity, which I've not yet defined, which I will call the capacity d minus 4 of the same ball. Okay, so this might, so we think, so let me say also that those two last results are with Perla Sosi, who is here, and Bruno Shapira. And they are work on progress, let's say. So not having the lower bound, we are not sure that's the correct scaling. We believe it's the correct scaling, but we don't have the lower bound. For diffusions, lower bounds are easy. You just find a scenario and you make enough excursions and you fill some balls, and that's easy. For percolation, it's very hard to find the lower bound because you have to explain how to explore, how to fill space. And so that's a difference between percolation and diffusion. Though the same, so I wanted to write this board because we see the same object, which did not appear so much in this conference so far, which is the capacity. So let me just say a few words about the capacity and what does this result means. When you see that, it means something about the way the two walk produce this intersection. So let me say a word about capacity. Yes?
This is just the result of the probability.
Yes.
Right? But you also said something about the shape of the set of t's. Is that going to go on?
Yes.
The shape of the set of points.
The shape of the intersection. How do they realize this intersection? Yes. But when I will give you some more things about capacity, that's going to be clear. So, what is capacity?
The other two parts of the theorem are in a different dimension? Or?
Yes, sure. This is just because it's defined only in dimension larger than 19 by Van der Hofstadt and Yarai, but it's believed that it's the same type of object. Those two are driven by the same decay of the green function. Okay, And probably if you give me a model, where a good enough model, we could derive such a bound. That is, if you know the two-point function, if you know that you have BK inequality, then something, we could find something like that. Okay, so it might be more general. Capacity. For simple random walk, the capacity of a set is just the limit. It's a hitting probability. So it's a probability that you hit the set when you start from far away. So I'm taking my walk, and you normalize by the probability that it hits 0. This limit exists, and then dimension are equal to 3. Okay, so that's the way I think about capacity. It's a hitting probability. The branching capacity, there is a nicer formula, which is a dual formula, as you in reverse time. And so this allows me to give you 3 different formula for capacity. You sum over all y's, and you take the probability that my infinite tree, but just the, let's say the future of this tree, starting at y, avoids lambda. You have the same formula for simple random walk. You could write this as that. Okay? And this was defined recently by a student of Omer Angel, Qingshan Chu, maybe 1916, in his thesis. And
why in one case is it hitting, in the other case it's avoiding?
They are dual formula. You want to hit, but if you reverse time, you will have a trajectory avoiding. So I could, I mean, you see it very easily with a last passage decomposition. Writing a last passage decomposition, you will see it. And for the percolation cluster, I would say that the capacity I'm using, capacity D minus 4, or capacity beta in general, and there I use what analysts would like. It's a soup. All loose are the same, are different faces of the same object. I'm just giving 3 representation of it. Sum of all the phi such that your green function with decay j star phi is less than 1. Okay, so that's another representation, and people working on there is still another thing, but so here it's more general because I take any green function. What do I mean by GB of x? Something which would decay like x to the beta. Okay, so this is the one which comes in here. That's the one which comes here. And let me say that for simple random walk, it's easy to see that all those formula are the same. Let me give you some a very quick way to see it. Do a last passage decomposition. Start somewhere and wait until the last site of visit of my set, y. So write the probability that S starting at x hits lambda as you say y is hit at time n. Okay, so and afterward you escape. So what you get is a sum over all the possible escape time. What you have is the number of visits because you had n number of visits from x to y. And here what do you have? You have the probability of avoiding lambda. So now divide this by g of x and take x to infinity. The probability that you hit from infinity, this is basically g of x. So this goes to 1, and you have the sum of avoiding lambda. Okay, and this is a last passage decomposition. Let's say that we don't have a last passage decomposition for branching random walks. So if you don't have that, it was hard to show that the branching capacity had, for example, a variational formula. So everything breaks down. All the sequential way of visiting a site breaks down for branching capacity. So that's the difficulty to work with branching capacity and with branching random walks. Okay, so now why did I say that as soon as I would tell you what's capacity, you would understand this formula? I'm missing just one way that probabilists like, which I guess explains everything. There is one. Place where capacity comes in. Imagine you random walk, so you fix. Imagine you have a set and you have a resolution rho. That's the scale at which you are going to probe your set. And what you ask about your random walk is that it spends a time rho in each of those balls. So a time rho or a density rho. Let's say that I'm asking that in each ball you produce density rho. Okay, I could have written it with the local time. This is less than exponential minus rho times the capacity of the union of the balls. That's a key estimate, which shows you that when you ask a random walk to uniformly visit a region at a given scale R, and R does not appear here, well, that's my set, what you get is the capacity. So not going to show how to, maybe you'll see how to prove such a result if I have time, but look at that now. That's exactly the same type of things. I have the capacity of a ball. So this suggests that the way the two walks meet a lot is that they spend a time or a density of order 1, because this is just a positive constant, in a ball of volume T. So I'm claiming that this, and we have such a statement actually. It means that the two walks spend their time T 1 over D, spend a density rho. So what I don't know is what's the radius. It might not be 0. But both of them go to some ball, and they fill up to a given density. That's the way it happens. So they're not going to meet on low density region. Okay, so you have to show that. But let's tell you a little bit how you obtain such a thing in general. So I'm not sure, any questions or? I did not give any statement about what the walk are doing under the event that they meet a lot, but we have such statements. But this is what you have to keep in mind. They need to meet in a given ball of density 1. There's no other scenario is okay. So how do we?
Can I actually ask a question?
Yes.
The way I would have approached this would be to condition on one of the processes and try to integrate it with the other. Basically reduce it to just the question about one process in a potential.
Yeah.
Does that lead anywhere? Because
Yes.
that might give you like the conditional statement.
Yeah. So that's in a way this is the way we do actually. But before that, what we need to control is how a walk is going to do some excess folding at all the scales. So I mean that. So I'm not going to. Your idea is what we are following, but before that there is something else that is that we need to control the excess folding. So what does it mean? So the way we do that is we fix a scale R. So I'm giving you our hammer, something that is going to be useful in all the problem of excess folding. Rho is a radius. Rho is a density. R is a radius. I'm rolling the ball over my trajectory. When the density is bigger than rho, you draw it in red inside. So what do I form? Out of my range, I take all the sites such that the density around the sites, the parameter n was the time I'm looking at. Now, BR, intersected with the range up to time n is above rho time RD. So I'm cutting all the high-level set of my occupation of my range. Okay, and I need to control. What I need to control is the size of those sets. So I say that there is an excess folding if you have too many sites which are doing something abnormal. Okay, so I need such a bound. The difference with the bound that I brought here, this key estimate, is that here I had fixed those balls, whereas here I don't know where they are going to happen. Okay, so basically, if you have L monomers or sites of your work where the density is high, it means that you have basically M disjoint ball, L over, because each site is surrounded by rho RD. So you have M disjoint ball where you will have a density rho. So you have the same picture. The only difference is that now the balls can be anywhere in a load by the working time. And that's why now I'm introducing a time to reduce the, because it would be probability 1 to do something in infinite time. So disjoint balls where I have a high density. Okay. So, so when you want to find such an estimate, you have to count how many ways I have to put those balls. And there is maybe n to the d to the power your m. And here I told you that I have this hammer, exponential minus rho capacity of my union of balls. My unions of ball. So I have, and this is basically each ball is of radius r. Its capacity is r to the d minus 1, and I have the capacity of m. I didn't tell you, but the capacity is always larger than the capacity. The capacity of a ball is of a radius r is r to the d minus 2. So I have here m to the 1 minus 2 over d. I don't know if this is too low to write here. Or, wait, let me. Let me rewrite it. I want to say that I have a combinatorial term, which is exponential m, the number of choice of my site in this ball. So the number of choice of my centers. And now I was saying that I have a nice thing, which is the capacity, that is r d minus 2 time capacity of the centers, which brings me just this. And most of the time, this beats this. And so the very simple observation which allows to treat infinite time is the following lemma. In any set of ZD, there exists a subset much smaller who has the same capacity. So such that the capacity of U is about its volume, which is about the capacity of lambda. So it means that instead of taking so many balls, I'm going to take much much less poles, to reduce this to be of the same order as that. This is going to be the capacity of U. And here, the volume of U is going to be of the same order. So this simple observation allows you to get some very efficient way to control the probability of those events. Okay, so that's the first observation. And the second one is that typically, when we want to obtain such a thing, the way to do is to compute the moments of the local time. And what we do is you take your local time of any process. Let me look at, let me call this to be the local time of my percolation cluster. I claim that if you have the nth moment against the test function of your local time, then you have the probability to spend some time in some region by Chebyshev. And for that, there is an important paper of Eisenman and Newman, and very old paper, where they did it for percolation. But they did not do it against the test function. They did not optimize. And if you do the correct thing that one has to do even in percolation would be to obtain this type of bound that I wanted to do, but I'm not sure I'm going to have time. J star phi of z if, and I'm now with the percolation business, for any phi such that the green function of the incipient cluster of the function phi is less than 1. So I claim that there is a very simple way to obtain an induction on the power of the local time against any test function which satisfies that. And you see that when you are going to take a soup, well, I've not yet written, but this is the right condition which define the capacity. Capacity was the L1 norm of a phi over this constraint. So if you have that, you're done. I mean, that's you do something more efficient than Eisenman-Newman. As simple, but more efficient because the capacity pops up.
Does this assume the triangle condition?
Yeah, this assumes a big K, that big K inequality. No, you don't assume. I mean, we know that you need BK actually. You need BK, and you need the 2-point function estimate. So the only thing, exactly.
Well, that's implied by the triangle condition.
Yeah. So if you have a model where you know that x and y decay like 1 over x minus y to the beta less than d, let's say. If you know that you have k, then you get that. And it's not going to be g star g, but something else. Okay? So, I don't know if I could show that for n equal 2 to convince you where does this condition comes from and why is it simple. But it depends, I think. I have 3 minutes? 3 to 5 minutes. Yeah, 3 to 5 minutes is enough to do the proof. For n equal 2. So for n equal 2, I'm taking the square. I didn't even say what's the scalar product, but it's the sum of phi of, let's say, x, when x is linked with z. You take this square, and you want the expectation of that. So you have a sum of phi x1, phi x2, and you want that your side z is connected with two sides, x1, x2. And it's a double sum. And this is a probability because I took expectation. And now when Z is connected to two sides, what you know is that there is always a Y somewhere on this trajectory. It could be X, it could be Z2, it could be X1, such that those three things are disjoint. Okay? So I'm not going to write that they are disjoint using disjoint edges. And then you can use BK. So if you use BK, you're adding this sum over Y, X1, X2. I know also that it's bounded by the green function. And now you have this G of Z minus Y, G of Y minus X1, and G of Y minus X2. And the key is that when you sum over Y, I shouldn't have put the sum outside, but I bring it inside, a convolution is going to appear. You will have one convolution and one G of Z, because I'm thinking of Z far. I want to do the infinite cluster, I want to put it to infinity. So I keep this one. So this is always bounded by G of Z minus X1 times the convolution of X minus Z minus X2. So you have a formula like that. And therefore, if you know that G star G of phi is less than 1, you integrate it, disappears, you end up just with less than a constant times J star phi of Z. And so, and the key is that all this computation is going to be depend on bifurcation, type of bifurcation. And so it's easy to be convinced that if you take the nth power, you still get here power 1 of the. So this shape of the induction, I believe, is much simpler than what they proposed, and catch the capacity. When you do a Chebyshev, you write by Chebyshev, you get something nice, that is the probability that you connect to a certain number of points is going to be bounded by, I can even ask that you spend a given time in given balls. You will get exponential minus the peak of the D minus 4 capacity of this set as you optimize over phi. So it's that's what I wanted to present you. Thanks a lot.